look at the situation where I have many layers of soil that are different and see what the impact is for our pile design and our evaluation of pile capacity. So notice I've got sand, then I've got clay, then I've got sand, then I've got gravel, I have the water table at the surface, and I'm applying 10,000 kilonewtons to this, and it's a square pile, width of 0.5 meter. Here are my soil properties, my densities, C prime, phi prime, SU over sigma prime I, and my K. Okay, so I'm going to find Q ultimate at t equals 0 plus, and I'm going to find the factor of safety. I'm going to use a delta that is 2/3 phi prime and alpha of 0.8. And so what are we going to have? We're going to have what? Well, at t equals 0 plus, I'm where? I'm undrained in the clay, because it's t equals 0 plus, but in the sand and the gravel, I'm going to be drained, because it's always drained in the sand and gravel. So my clay undrained failure envelope is that. My sand and gravel failure envelope looks like that. So what we have to remember when we're doing the drained, normally we do what? Tau FF is sigma h prime tangent phi prime, but what are we concerned about? This delta, which accounts for the smoothness of the pile, it's going to be sigma h prime tangent delta. So in other words, my coefficient of friction is tangent delta, not tangent phi prime, because of the smoothness of the pile. Okay, so let's look at the solution. What does it look like? Well, I have to do my depths. And what do I have to do? Because my K values are all different, which means what? I have to consider the boundaries between the soil types. And so I'm going to have what? This is at 5 meters, so I've got a 5 minus 5 plus. This is at 8 meters, so I have an 8 minus 8 plus. And then the base is at 12 meters, so I write down 12 minus, but it's 12 meters. So we do our usual sigma V, and notice I kept everything easy. Everything gamma saturated is 20. So we have 100 at 5, we have 160 at 8, and then we have 240 at 12. So very easy to get when all our gammas are 20. The U, you can all get that because it's the ground surface, 9.8. Don't forget to use 9.8. So 5 times 9.8 is 49. 8 times 9.8 is 78.4. 12 times 9.8 is 118. So we have our U's. We get our sigma V prime, of course, is sigma V minus U. Now I have my sigma H prime. Well, what do I have to do? I have to use my K values. Now, notice I don't even give a K value for the clay. Why? Because we're going to use the undrained shear strength there, which we're going to get from SU over sigma prime I. So remember, in the clay, we're total undrained fast, so we're doing total stress analysis. I don't need the sigma H prime because I'm doing total stresses. So okay, but let's look at the sands here. Notice I don't need to do anything with the gravel. Why? Because the gravel is below the tip. It's not next to the pile. It's not on the side. So I just have what? Sand, clay, sand down here. I don't have the gravel. It doesn't appear because the gravel's below the tip. We're going to use the gravel when we analyze the tip resistance. Right now we're just doing the side shear. So I'm going to use that 0.7 and that 0.5. So I have 0.7 there. This one's 0, so I don't need to use anything. And I'm going to have the 0.5 is what? It's there. So that gives me my sigma h primes. Then what do? Well, then I need to use sigma h prime tangent delta to get my tau ff. So my delta is 2/3 phi prime. So I'm going to have sigma h prime tangent 2/3 of 30. Sigma h prime tangent 2/3 of 35. So I had 30 up there, I have 35 down here. And 61 tangent 2/3 of 35. So I get my tau FFs right there. Now, how do I do it for my clay? Well, for my clay, I'm going to use the SU or sigma prime I of 0.4. So my sigma prime i's are 51 and 81.6. So it would be, 0.4 times 51, 0.4 times 81.6, but then I have to put in this alpha equals 0.8 factor. So the alpha factor, I need to put that in. So that's where the alpha factor goes. So I multiply all that times 0.8. Again, that accounts for smoothness of the pile and disturbance of the clay and stuff like that. So that's the way I get all my tau FFs. So there they are. I just redid the table here. And now I'm going to take these values and I'm going to plot them. So I plot one after another in sequence. The 13, let's do it one at a time here. So this is the way you have to do it. You got the 0, 0, 13. Connect a line. Then 16.3, connect a line. Then 26.1, connect a line. Then 17.6, connect a line. Then 26.3, connect a line. You have to do it in that order so that you get the right, in other words, you don't want to go like this, to 16.3 and then back to 13. And then over to 17.6 and then up to 26.1 and then down to, you don't do that. You have to follow in this order, point after point, and then you get something that looks like that. It looks like a Christmas tree. So what do I have to do? I have to find the volume of that and get the total shear resistance. We're going to call it Q side. So in other words, one of the things I want you to learn from this example is that when we're doing the side shear and we have clay undrained, which is TUF, tough, then my tau FF is going to be SU over sigma prime I times sigma prime V. For clay drained, which is EDS, EDS, then I use my drained envelope. And, we're putting in all these factors. So there's a factor there, but then I've got factor and factor here times phi prime. So what do I mean by the factors there? Well, the factors, the delta is a factor times phi prime remolded, and phi prime remolded is a factor times phi prime. So, I call them factor 1 and factor 2. Eventually, you have to multiply them both out onto phi prime. These are going to have to be given to you, so you just pay attention to the factors, and this is where you put them. This is where I put alpha. You just have to know where to put those factors, basically. And again, when I'm into sand drained, well, I don't have the remolded issue. So no remolded issue for the sand or gravel, because we don't talk about remolding sand or remolding gravel. It's a different issue. So why? Because we don't consolidate the sand. We don't consolidate the gravel. And this remolded factor, this remolded friction angle, has to do with the change of the friction angle due to consolidation, due to disturbing it and then reconsolidating it. So it's both a combination of both of those. So we just take a delta factor here for the sand drained, and we take the tangent of the factor times phi prime. Now, when we do the tip resistance, though, so let's get that part right. Remember, when we have clay and drain, which is tough, total and drain fast, we use, remember we had a trick with the C prime in our equation. It's going to be SU over sigma prime I times sigma prime V. It has nothing to do with phi prime, C prime rather. That has nothing to do with C prime. But, you know, the way we write our bearing capacity failure equation, we have this C prime there, and we have to use it even though we're in tough, but that, remember, C prime means SU. So there's my calculation of SU, basically, for the tip resistance. Now, we don't have to do any of this phi prime remolded, and we don't have to do the delta. Why? Because we're talking about the tip, which is below the pile. We haven't remolded the soil, well, we haven't exactly remolded the soil below the tip, whereas we have remolded the side. In a sense, there's damage to there's damage to the stuff below the pile tip, but not as much. And so, you know, we're just going to go with SU over sigma prime I times sigma prime V. Then that gives me my, you know, that C prime, which is SU. And then my Q, well, it's total. So it's going to be a total stress. Now, I'll show you how we use that. But and then what do we get? We get our NC star and NQ star from using the chart with phi equals 0. Whereas when we have clay drained, C prime is C prime. Q is sigma V prime. It's effective. Effective. Why? Because we are in effective drain slow. So it's effective. Over here, it's total. Total. Because it's, you know, total on drain fast. So then when we're in clay drained, what do? We get NC star and NQ star from the actual value of phi prime, not 0. Up here it's 0. Why? Because we're total on drain fast. In the sand drain, C prime is 0, so we don't have to worry about that. My Q is going to be a sigma V prime. And we get NQ star from phi prime. So the sand is easy. It's the clay that causes the problems here, clay and silt. And so back to our example, this is our Christmas tree, in a sense, that we have to get the volume to find the total side resistance. And then, so I'm going to leave that for a second, and then we're going to get our tip resistance. Well, remember, the tip is in gravel. So if we look back at our, that's what we pay attention to when we do the tip. We don't even pay attention to those soils because I'm looking at the soil below the tip, and that's gravel. So I'm using my gravel, and since C prime is 0 in gravel, I can get rid of that term, and all I have to do is worry about that. And as we said, the Q is effective. Why? Because we are in the gravel, we're EDS, effective drain slow. So we are looking at the effective stress at the pile depth. So we've already, interestingly enough, we've already calculated that Q, that 122. Where does it come from? Well, we've calculated the effective stress at that depth right there. At 12 meters, we got the sigma V prime. So we're going to use this for our Q and NQ star. So we've already calculated it, so that's nice. So we have the 122 there. We look at our NQ star at our friction angle comes up with 900. So NQ star is 900 from our chart. Let's just take a look at it. I guess we can go back. Remember, we use the phi prime in the gravel. So the phi prime in the gravel is given to be 45 degrees. So we go to our chart and, oops. Okay, it's taking a little longer than I thought. All right, it's probably the next one. Nope. We go to our chart and we're at 45 degrees, so we're way out here and we're picking our number. It's pretty close to 900, so that's what we're going to use is 900. You can see how big it is. And so 122 times 900 gives us 109,800 kilopascals. And the area of the tip is half a meter squared, because why? Because if you remember, the pile is a half a meter width and it's square. So the tip area is a half a meter squared. And so that gives us, I multiply those out, I get 27,450 kilonewtons, and then I'm just going to make a very quick estimate of my side resistance. So I'm showing this little trick because sometimes you need to get a quick answer. I don't want you to do this on quizzes or exams or anything like that, but when you're doing a design and you don't know if this is going to work, and you're going to have to redo this in a sense, you can get a quick answer by, when I draw this out, instead of drawing it perfectly and taking all of these, let me make a quick estimate by just sketching out, if you draw this to scale, sketching that out and trying to figure, and just using this triangle here. So, sometimes this is convenient. I want a quick answer. I don't, in a hurry. I'm trying to tell a client, I'm sitting in a meeting here and the client wants to know, what do you think the pile capacity is for this? Well, a lot of times you don't have time to do all this little detail stuff. So you make some quick estimates and give their client a ballpark figure. Is it going to work to put down the pile to that gravel? I want to know. Give them 5 minutes. Tell me, do you think I can put down the pile down that deep? And you have to make an estimate. Now you can amend your estimate to your client later, but you should have an answer. It looks like it's probably going to be feasible, but let me check it out in more detail. That sort of thing. So now I have a triangle, which is 1/2 the base times the height. I've chosen 30 down here to make it doesn't cover all these little jigs and jags. So 1/2 times 30 times 12, that's the area. 12 is here, 30 is there. 1/2 30 times 12. And then it's 0.5 meters perpendicular. I can't show this, but if I were going to draw this square pile, in a sense, that's not perfect, but it's 1/2 meter perpendicular to the paper. So that's where that half comes from. And then we have 4 of them. So I get 360 kilonewtons. So now what do we see? Here's my tip resistance. Here's my side shear. Obviously the side shear makes almost zero difference. So even if you had gone through and gotten all of that, well, we knew it was an end-bearing pile, and you may have gotten an answer a little bit different from 360, but your end result is going to be very little changed if you would put in all the details there. So that's one little advantage of doing this. Okay, so, in this particular case, let's just say, suppose we consider that the pile weight, concrete 26 kilonewtons per cubic meter, is already on it. In other words, it is already on it. We have the pile in the ground. How much does the pile weigh? Well, I figure out how much the pile weighs. The volume of the concrete times the volume of the concrete times the unit weight. And we end up with the pile weighs 78 kilonewtons. So I can subtract off the 78 from that number, and makes almost no difference. So in this particular case, the pile weight has no impact on this, almost no impact. And we get our factor of safety by taking that number and dividing it. We put on, if you remember, we put 10,000 kilonewtons on this pile. So there it is right there. We were asked for the factor of safety. If we put, 10,000 kilonewtons on that pile, and our answer is that our factor of safety would be, approximately 2.77. So pretty close to 3. It sounds pretty good. Okay, so now, so it looked pretty good. Okay, now we're looking at the same profile and the same pile as we previously done. So same problem. But now I want to find the number of piles to get a factor of safety of 2.5 if my column load is 100,000 kilonewtons. So in other words, I'm trying to, I've got my pile cap here, got my column and my pile cap, and I'm applying 100,000 kilonewtons there. I want to know how many piles do I need here? What's the number of piles there? So we don't know, but we can figure it out here in the sense that, well, for each pile we get 27,800 kilonewtons, and our factor of safety is going to be what? The capacity of all the piles divided by the column load. Well, we want to get what is the capacity of all the piles. So I'm solving for this here. I'm solving for that capacity. And the capacity then is going to be what? It's going to be the 100,000 times the 2.5. Gives me 250,000 kilonewtons. And in a sense, we're getting going here. So the capacity is what? It's the number of piles times the Q ultimate for a single pile, n is the number of piles. And so I simply I have the capacity of 1. That goes down there. Capacity we need. And we end up with 8.99 or 9 piles. So we need 9 piles, and you can lay it out here. There's my pile distribution under my pile cap. So some of you are asking, how do we get the number of piles? Took us a long time to get here, but that is basically what we do. We want to space these out maybe approximately 2b distance from 2b edge to edge, and so so we space them approximately 1 meter apart edge to edge, and that means that that distance is 1 meter, that distance is 1 meter, that's a 1/2 meter, that's a 1/2 meter, and that's a 1/2 meter. So what does that add up to be? That's 3.5 meters edge to edge. So from edge to edge here, we end up with about 3.5 meters. Spacing them about 2b. That's approximately normal there. Spacing. Now we're going to talk a little bit about, this calculation of n here in a second, and so, okay. Now, what we didn't take into account a little bit is this. Now, the way I want you to envision our issue is that envision that there is a little space down here. In other words, I don't put my pile cap all the way to the ground. And instead, I just get a little space. Now, if I'm loading this, you can clearly see that this pile cap has no influence on the capacity down here. In other words, it's only the piles. If you envision this, then you can see that only the piles hold this thing up, not the base of the pile cap. So the base of the pile cap has nothing to do with it. If I do that, then you can clearly see, or you can see that basically, if I take the number of piles times the Q ultimate for the group, or for the individual pile, so take the number of piles times the Q ultimate for an individual pile, that's going to give me my capacity of the group, except that these piles are not spaced that far apart. And so if this pile goes down, it's going to bring soil in here with it. And that means this pile is not going to get the full capacity in a sense. So what people do to account for this little, the effect of the piles being sort of close together is to reduce the group capacity to be 2/3 of n times the Q ultimate for 1. So what we did previously, conceptually okay, but now I would want to put in another fudge factor there, 2/3. So that I'm going to get a reduction here, and then I need more piles, and I'm not going to go through that. But okay, so the way that we look at these pile groups is we look at two different ways they can fail. Or, these are a couple different ways. You always have to think of a lot of different ways things can fail, but the way we do it typically is they can fail as a group like this, or in a sense individually failing of the piles, and each pile sort of works independently except for 2/3, and that's our capacity of our group. Or what can happen is that this whole thing can act as a block. And so I look at this block here, and I'm worried about a block failure. So in other words, I'm looking for a bearing capacity failure of the block. So you take this, envision this solid concrete, for instance, and that block of concrete will fail like we normally expect it to fail. And we sort of treat it as a deep footing. So in a sense, we analyze this like this, a big, deep footing. And if we do that, then we go back to our bearing capacity equation. We're just going to look at the tip, for instance. Now there's some side shear here and that you can take into account also. But right now I'm just going to look at this as a deep footing, and so we're going to get failure underneath here. Now in reality, what we find is it doesn't quite fail like this when it's really deep. That's about all I can say. The failure surface is going to look sort of funny. I don't want to get into it, but it's not necessarily the nice clean failure surface that we have sort of been assuming. So there are some problems with this when you go to deep footings, but no matter, that's the way we look at it. I want to say a couple other things. Now, here's the thing. The pile analysis, again, is very inaccurate in a sense. It's not reliable. People have found it's a good starting point, but you're not going to get an exact answer with that. So a lot of times we do, if we have an important job, we do a pile load test. What is that? You take one of your piles out into the field. Now, hopefully you can get, at this point you haven't designed the pile, so you don't know exactly what it's going to be like, but try to pick a pile that's sort of what you expect it to be. And then you put it into the ground. Then you have to have other piles that act as tension piles. I'm going to put a beam across here. It's actually another design that you have to do to design this pile load test, and you have to put a frame around it. I said beam, but it's really sort of a frame because you generally have 4 of these piles. So in plan view, your pile load test is more like, like this, and one in the middle, something in your test pile in the middle, and so this is what we call a tension pile. Why? Because what we're going to do is we've got our pile in the ground. We put a jack between the test pile. So this is the test pile. That's what we want to find out, is what's the capacity of that pile. And it's between the jack and the frame. And we're going to pressurize this, and that's, it's going to do 2 things. That jack is going to push that pile down, but it's going to pull these points, and these points are going to move up. So that point goes down, these points go up. If these points are going up, then this pile is in tension, and this pile is in tension. And so we have to design this so that the side shear on these tension piles, on the tension pile of the piles, is enough to resist and give us the capacity to push down on this pile here, so we can test its capacity. So how do you, what's a tension pile? Well, a tension pile is you just have, you don't have any tip resistance. All you have is side shear. And I'm just going to tell you in advance, even this is not a complete answer, because you're going to measure the load, you're going to measure the deflection. So you measure the load you put on there, and you measure how much that moves down. So you get sort of a stress strain curve out of it. Again, load is on the y-axis, deflection is on the x-axis. It looks like a stress strain curve. The only problem is it sort of doesn't have a nice peak usually. So it'd be nice if we had something that looks like that, and then you sort of have that in a way as your peak, and that gives you your capacity. But generally, we have a limiting deflection. We don't want too much deflection. So you get an allowable value of deflection. You come up and you get your capacity basically from the deflection restriction. So, okay. And I'll just say one other thing about this, in a sense, is that another issue with piles is when you drive a pile, what happens? You tap on this pile, and you're sending a compression wave down that pile. That's what that's showing. And you get to the bottom, and then it extends the pile in the ground, and then it can send a tension wave back. And if you're not careful, you can actually damage the pile in driving. You can bang it too hard. The compression wave can be too great. You can get a tension wave, because concrete doesn't do well in tension, for instance, if it's concrete pile. So be careful in pile driving. So that's sort of a message of that. All right, I'm just going to go to the next. Okay, I'm going to stop there.